Again. Today we have actually two topics which are almost independent, but they play a role tomorrow. So the first one is the question, why is the chromatic polynomial a polynomial? And you know already one answer, because there is a proof, and I've shown you the proof. But there will be a different answer. And then we want to see, as we defined it, there are too many graph polynomials. I mean, we have too many degrees of freedom. So I want to introduce somehow logical formalism. And I will give you a very, very gentle introduction, even if you don't know, almost no logic, what I mean by logic in graph theory. And the natural language of graph theory, at least for finite graphs, is not first order logic, but is second order logic. And you will see that in many ways this is the way you think about it. So maybe we also make a 5-minute break when we get started. So first I want to discuss a bit variations on chromatic polynomials. So we have seen the classic chromatic polynomial. Now the variable is called lambda, like in the historic literature. It's any indeterminate. And Birkhoff's theorem says that the number of proper colorings with at most L colors of vertices is a polynomial in lambda. And here is another very short proof using deletion and contraction. And this was kind of the beginning, and when people discovered this, or especially when Birkhoff discovered this, he was very excited, and he hoped actually to prove the four-color conjecture using algebraic properties of this polynomial. And I also showed you that this polynomial has this funny additional combinatorial interpretation, that if you ask, now by reading the definition stupidly, the number of colorings of G with -1 colors, and it turns out that this has a combinatorial interpretation. I've discussed this, and he also showed it for every M, and I haven't seen any combinatorial interpretation for rational numbers. So if you want, I'm sure this would be a very worthwhile paper, or at least a note in some combinatorial paper. I have found an interpretation for lambda equals half, or lambda equals pi, or I don't know, whatever. So it's not known. Okay. Now, as I also said before, this is a quick resume, how this relates to the four-color conjecture. So the four-color conjecture says that, or the stronger version of the four-color conjecture of Birkhoff and Lewis, which is still open, says that for no planar graph G, could it be the case that lambda is a zero of this polynomial, real zero, if lambda is in the semi-open interval 4 up to plus infinity. But it has been shown for 5 up to infinity. And Jackson has analyzed the location of where there are no roots, so there are no we have no roots for arbitrary graphs between -infinity and 0. This just follows from the way it is defined. And then between 0 and 1, where you have to do something, 0 is excluded here, and between 1 and 32/27. And it is still open what you can do between 4 and 5. And Thomason and Sokal have shown that the real roots of all chromatic polynomials are dense in the remaining interval, where k is the tree width of a graph. And there are other versions of this. Actually, if you look at what does it mean dense, it means for every epsilon there exists a graph such that the chromatic polynomial has a root in the for every epsilon and every point there is a graph such that the chromatic polynomial of this graph has a root in this neighborhood around the point. Now, the first time I presented the theorem which will follow at the conference, I was aware of colorings in a new way. And maybe as a man I would give you the following example. Normally you don't notice that women in the streets are pregnant, but if your wife is pregnant, then all of a sudden you see that everybody is pregnant. So here, or similar things, I mean, whatever it is, if nobody pays attention to the color of a hair randomly, but if you have green hair and all of a sudden you see everybody else who has green hair. So I went to this conference and I was kind of allergic, I mean, alert rather, not allergic to colorings. And I found several colorings which were given talks about in the same conference. So obviously you can look at edge colorings, which is to say you color edges instead of vertices, and they are proper if two edges have different colors when they have a point in common. Now this we'll see is rather easy to see that this is also polynomial because the edge colorings is the same as the vertex coloring of the line graph. Total colorings is where you color both edges and vertices. You can have connected components where you require that whenever two points are connected, related to each other, they must have the same color. Then there is somebody who wrote even a book about hypergraph colorings, where he claims that hypergraphs and colorings together are as good as linear structures in some sense. Anyhow, at the same conference where I was, there were more colorings. Somebody gave a talk about convex colorings. Every monochromatic set induces a connected graph. Injective colorings, F is injective, the coloring map is injective on the neighborhood of every vertex, so you have different colors around the point. Coloring is complete if every pair of colors occurs along some edge. It is harmonious if F is a proper coloring also here, and such that every pair of colors occurs at most once along some edge. Equitable, all color classes have almost the same size, and then you can modify this so that you don't have to round off. And here is a fact which follows from our theorem, that all the cases which are starred are polynomials. If you count the number of such colors, are polynomials in the number of colorings, and those which have minus are not. But it went on. The same conference I heard more lectures, and somebody talked about path rainbow colorings. F is a edge coloring, is path rainbow if between any two vertices there is a path where all the edges have different color. There may be another path which doesn't. And then we also found out that this has been defined in computational biology and has a natural. So we found out that this is also corollary to our theorem. Then we have monochromatic components. Instead of saying that every color set every color set is an independent set. I left the chalk here. Yes, here it is. Every color set is an independent set. This is proper coloring. And then you can say, no, in my case, I'm a bit more generous. I allow connected components of the induced graph of size at most 2. Or I allow connected components of size at most 3. Things like this. Okay. So these are called MCC colorings, and T is the parameter of the maximum size of the connected component. And for each T, the number of colors again gives a parameter invariant for graph polynomial. So they spoke about this in terms of extremal graph theory, but I noticed that, you know, these are all corollaries to my theorem. And here is some reference that these are not just crazy colorings, that people spend time writing papers about it, and there are even more papers written about it currently. So here is a more general definition collecting the previous things. So now you take P is any graph property you like. Planar, Hamiltonian, what do you like?
Bounded in some width.
Bounded in width, okay. Whatever. You favor your property P. And then we make we look at the following. We define a coloring function where we request that the union of n color classes induces a graph in P. So here in this case is always the union of one, yes? But you have in the literature you will have acyclic colorings where it says that the union of two color classes induces an acyclic graph. And this has been studied already in the 70s. Okay? So indeed, for n equals 1 and P the empty graphs, you get the proper colorings. For n equals 1 and P the connected graphs, you get the convex colorings. For n equals 1 and P the graphs which are disjoint unions of graphs of size at most t, we get MCC colorings. For n equals 2 and P acyclic graphs, you get acyclic colorings. And just to show that this is not my imagination, somebody in 73 already wrote a paper, and you can see the follow-up things. So here is a theorem for every n and for every p, the corresponding counting the number of colorings is lambda many colors is a polynomial in lambda. So now all of a sudden, I didn't show you the proof yet, but we will discuss it, but now all of a sudden you wonder, can you prove this? I mean, so if you come from Birkhoff, you say, well, I have to look for deletion and contraction, but at least for one of them it won't work. I mean, or actually for none of them I know it to work. So what is the secret behind, what is the secret? Why is the chromatic polynomial a polynomial? Yeah? I mean, and the answer there is deletion and contraction, but it doesn't give me any answer here. So all of a sudden I gave you many generalized chromatic polynomials, and you wonder why. Now here you can even generalize this. So the colorings by now were functions from vertices into colors, or from edges into colors. You could have also a coloring relation. So for instance, each vertex is given two colors, or each vertex is given any number of colors from a certain set. And you can play around. So we don't want to play around too much, but actually the framework which I will describe to you is even more general. You don't have to do this in general. But here is a case which is interesting to see, because this is a generalization which is relevant. So somebody introduced colorings, Domen, Pönitz, and Titman in 2003, which do the following. We look at two different color sets. You have good colors and bad colors. Okay, so K1 and B, A and B, and the one is of size K1, and the other one in their presentation is of size K1 plus K2 minus K1. What you can also substitute here. And the colors in A are proper colors, and the coloring function requests that you have a map from vertices into a set of that many elements, which is K, such that if the color of 2 is in the A colors, then they cannot be neighbors, and if the color is in the B colors, they can be neighbors. And so this gives and Domen, Pönitz, and Titman proved that if you count the number of colorings of G with this type of coloring, and now they have a variable for K1 and for K, the way it is defined here, then this is a polynomial in K1 and K. And actually they use this to show it connected to some other things. But this is so you can have, well, we have seen already the Tott polynomial is not a coloring polynomial for our current point of view, but it's also a two-variable thing. But I wanted to show you a case which I've found in the literature, where you have really colorings which you have different colors. There's one color which is used for one application, and another color which is used for another application. If you distribute radio frequencies, this may be very relevant. So indeed, many applications come of applications of this type in electrical engineering. So I told you yesterday the anecdote when I met Professor Zilber, yes? So he said he looks at it as this way. Well, we actually. So now we take we don't have to do graphs, but if you prefer, if you are not too easygoing with arbitrary relational structures, think of it as graphs. So M is any finite relational structure with any number of relation symbols and function symbols. So tau to me is a vocabulary, is a set of finite relations and functions, and K is a naked set of K elements which serves as colors. Now, in our colorings, always the colors have no meaning. So if you are in the Cold War, you paint the Soviet Union red and America blue, and then somebody else paints America red and the Soviet Union blue. These are different colorings, but they are equally legitimate. I mean, if they are proper colorings, they stay proper colorings. So we are given an arbitrary structure, and we are given a set of K colors, and we have a map which maps tuples of my structure into colors. So you, instead of coloring elements, you can color edges, pairs of even non-edges. You can color triples, you can color quadruples. You fix what you want to color R. And we look at families P consisting of triples of this form. So we have structures which are given as a structure with a universe and its relations, a function from a Cartesian product of the universe into this naked set, and the naked set. You can make this the universe is the union of the universe of this and this, and then you have a predicate saying that I'm a vertex or I'm a color. So this is my structure. And then you can look at properties of structures like this. So this is just a family of objects of this form, which is closed under isomorphism suitable for this type of structure. So we have properties of these objects. And we say a property is a coloring property. And the way I started talking, first of all, if it satisfies the isomorphism condition for being a property, it satisfies the permutation property, but it follows from the isomorphism property, which says the following: if you permute the colors and induce the F accordingly, then if the original F was in P, then also the permuted F is in P, like my Cold War example. But the most important property, so this is not so. This is easy to do. I mean, this is nothing special. But here comes something special. So let me draw a picture. Here is my M. Here is my set of colors. And I want to use a color here also. And here is my F. And this situation happens to be in P, and now I do the following change. I add unused colors. Unused colors means elements in my naked set which are not in the range of F. You take your map from the Cold War, which has 4 colors, and you say, but I have a 5th color which I don't use. No country is colored like this. And then you want to say that the same M and F, but with this bigger set, is in P if and only if the original set was in P. Also the other way around. If you have unused colors and you delete them, then the resulting structure still is in P. So the property P has this extension and reduction property that you can play around with the non-used colors. So these are 3 conditions.
So the permutation property does not hold with the domain.
Which one?
The last one, permutation property. When you have a K1 plus K2 colors, your first K1 should have a different color.
No, you only permute the range.
Oh, so you can choose any set of K1 colors in the range?
In the range, yes. You are right. So if we go back quickly, you see, to be convex, doesn't matter if you take another color, but those which were in the range induce connected graphs, then this remains true. Injective, it remains true. Complete doesn't remain true, because here you say every pair of colors was used, but now I add a new color, and then the pair of unused together with a used color has not been used. So this is why this has a minus. Harmonious remains true. This has a funny name, but anyhow. We'll come back to this also tomorrow. Equitable obviously doesn't work because of conditions like this, but you can modify it and then it works. And if you continue, indeed, path rainbow has the property that if you have unused colors, then they are unused. You want to have a path where all colors are different. You have this path. Never mind that there is another color which you didn't use. Monochromatic components the same. So this is the condition we put on. And we get indeed, I will wait with this. You get indeed the following theorem. First of all, we define chi of P, of pi in this sense, is the number of colorings with k colors, which colors the structure M, or the graph, if you want to label graph, whatever it is going to be. And the theorem says, this is the reference where it appears, but the theorem says, no. I don't have the theorem stated. Anyhow, the theorem says that this is a polynomial in K. I don't. The devil has taken away the slide.
It doesn't matter what value R you have. Like,
no, it doesn't matter what value.
You assign like triples to a certain color.
No. The F has to be uniform. So if you color triples, you only color triples, and if you color 5 tuples, you color 5 tuples. And at the moment, this was a function. And if it is a function and the arity here is given of the function, then obviously the possible values of the structure, if you take an infinite set of color, is bounded. You cannot have more than some bound on F. But if you take F to be a relation, then it could be that this is unbounded. So we will have another additional definition. If we don't want this to be functions, but we want to allow these relations, then we have the initial property that the number of colors used in a given structure is bounded by the size of the structure, and then you can generalize the theorem also to coloring relations. So this is the explanation why. Here comes sorry, I found this here. There was some remark in between. Now the theorem says that for every structure M, counting the number of function is a polynomial. And actually this is how the polynomial looks like. So this is and it's amazing that Birkhoff was so happy with his deletion and contraction proof that he even didn't bother to see is there another proof of a theorem. But here is the proof, which is rather simple. I mean, if you present it like this and you build it properly, you can give it in the first 5 sessions of a graph theory course. We do the following. We take as a basis of our polynomial ring, we take not x to the k, but we take x choose j. If you put here the variable and here j running from here, you get a sequence of polynomials which also forms a basis. And then you do the following. You take as coefficients c phi of m and j is now the running index here, is the number of generalized colorings with a fixed set of j colors. But all of them are used. Okay? So what is the meaning of this? You have as many colors as you want. You choose your j many out of the k's you had. This gives this part. And then you give the coefficient in this way, and you get the polynomial. And to show that indeed this is well defined, you need the independence on the where you chose, it doesn't matter, and the permutation property of the range. So this is just needed to make this function. I mean, this is the polynomial you want, and you ask what do you know what do you have to know about phi that this proof works, and these conditions are just there to do this. So if you teach next time graph theory, you can show the 2 proofs of the chromatic polynomial. And the point is that the deletion contraction had an enormous impact on the literature. It was something extremely interesting to look at, and it developed in this way. But actually, this proof has the other advantage that it proves uniformly for many, many, many coloring types that counting the number of colorings is a polynomial. Now, the polynomials which are written in a basis like this happen to have a name in the literature. They are called Newton polynomials. But this is you can do transformation. So in the light of all this development, we call these objects, depending on some family of things like this, generalized chromatic polynomials. And the cases we have seen before all fit into this framework. Okay, so here I have in more words, I have the precision that the proof really works. So this
Birkhoff didn't know?
I don't know whether he know. He's dead. We cannot ask him. But even if he knew, it didn't interest him. See, it didn't occur to him to note that other strange colorings are and I think he didn't think of other colorings. He picked up this notion of proper coloring, which is very natural. And I don't think if you teach a course and you explain to people what is a proper coloring, and then you would a surprise exam, you would ask him, how would you define generally other colorings? They would be kind of confused. I mean, it needs a reason. And I'm not saying the theorem we proved is deep. The theorem is surprising that nobody did it before. And it's even more surprising that we found many of those. So for instance, the people who studied harmonious coloring where every pair of colors is only used at most once. They wrote a whole 70-page paper on harmonious colorings with many, many interesting things. And I met them at the conference and I told them, do you know that the number of harmonious colorings is a polynomial in K? He said, yes, we knew that. But it didn't occur to us that there is something interesting to do with this. So it depends. Now, to us, this will become interesting. I have these are the slides I had last time. There is a question of complexity. How complex is given a graph? How difficult is it to compute the chromatic polynomial, or rather the coefficients, or rather evaluations? So you look at the chromatic polynomial in this way. You look here. This is the graph, and now you put a fixed value x0. And you look at this and say for the moment x0 is a rational number. So for each x0, this is a property of a graph, or a value, a graph parameter. It gives a value. So some graph parameters are computable in polynomial time, like number of connected components. Some graph parameters are difficult to compute, like the number of 3 colorings, is NP hard, or actually the number of 3 colorings is even sharp P hard. And you can ask to classify these, so you have an infinite family of graph parameters, and you measure now the complexity of computing this function as a function of the size of the graph. So in this case, you get for x0 equals 0, this is in P. Trivially, for x0 equals 1, this is in P. For x0 equals 2, and P part it happens to be in, if you count the number, in sharp P. So deciding whether it is 2 colorable is in P, but counting the number of things is in sharp P. For x0 equals 3, it is in sharp P. And then you ask further. And the first observation is that actually these are the only cases which are in P, and every other case, even x0 equals 7/9, is in sharp P. So this has this funny property that actually for almost every value of x0, I come to you, this is hard to compute. And now you can ask the same question for any other generalized chromatic polynomial, which what the people, and then okay, I'll talk later today, or tomorrow I can talk about this. Yes?
What is sharp P?
Sharp P is a class introduced by Valiant. It's a counting class, but the important thing for you is that P to the polynomial hierarchy is a subset of P to sharp P. I mean, this is more difficult than anything in the polynomial hierarchy. So in particular, if you don't care about this, this is bigger. This is more difficult than NP. So for every point, computing for every value of x0, computing the graph parameter is at least as difficult as NP, with the exception of 2 points. And actually it is maximally difficult in some sense of a more sophisticated complexity theory. There are very interesting connections. There is a book by Dominic Welch on the complexity of computing the Tat polynomial and other polynomials, and there is a very interesting theory behind this. So all of a sudden there are many chromatic polynomials, and we have seen already the classical. These are the zoo again. These are the elephants and the crocodiles of the zoo: the chromatic polynomial, the Tat polynomial, characteristic polynomial, matching polynomial, then you can do a similar click polynomial, counting the number of clicks of size k, cover polynomial, which is an attempt to do an analog of Tat polynomial for directed graphs, never mind. Interlaced polynomials, which came back in biology, which are very popular. Sangil knows more about those. And then there are also, if you have labeled graphs, you have not polynomials in topology. So these are the prominent animals in the zoo. Now, how does our theorem relate to those things? So the way we define them, if we define them, they were not chromatic polynomials. They didn't look like generalized chromatic polynomials. So they seem to be a completely different category. I now gave you a way of producing many chromatic polynomials. I showed you a way of producing many generating functions as graph polynomials. But so some of them are of the type of generating functions. So how can we produce graph polynomials? Now here is just some advertising. So the graph polynomials really are not just an exotic object. They have applications in chemistry, biology, statistical mechanics, social networks, finance, mathematics. You Google things like Tat polynomial and finance, and you will be surprised what you get. Now we already started discussing yesterday, and even stronger than I've prepared the slides. One way of comparing polynomials was by comparing them by distinctive power. You say that two graph polynomials are somehow have the same distinctive power. I'm not saying they are the same from an algebraic point of view, but have the same distinctive power if whenever two graphs are not distinguished by the one, this is equivalent to saying they are not distinguished by the other. So here is a question which you can ask yourself. Take the case we had with your favorite property and say n equals 1. So each color class is in P. So if you have two different properties, P and Q, two graph properties, are the P colorings, or counting are the G, or the G P, G X, and G Q, G X, DP equivalent, or when. And I have an answer, but I leave it to you to think about it till tomorrow. So I gave you too many recipes, but maybe you say, Makowsky is really a bluffer. Most of them are actually the same. So you can think about it to show how would you show that those things are or under what condition are they really not DP equivalent. So anyhow, we can distinguish them by distinctive power. Now another argument which appeared in the literature, which I found this argument is usually used to show that your graph polynomial is different from mine. Now this is maybe difficult to find, but how do I show this? I give you two graphs where you distinguish and I don't distinguish, or the other way around, or both. So this gives a natural way to show things are different. And now how do you show that two very strangely defined graph polynomials actually do not distinguish different things? Well, easy in quotes. You say for every graph, but this is too much. You don't want for every graph. So people looked at an argument without looking at this. They looked at the argument. They wrote a paper where they wanted to show that, you know, hurrah, my graph polynomial really is the most general among all those. And what they actually used as an argument to make precise what they mean, they said, if you know my graph polynomial and you have the coefficients, there is a uniform way of computing your coefficients. Okay? So not just from, so there is one algorithm which, given a graph and the polynomial for my graph, I can compute the coefficients of your graph. And a stronger version of this is, where you can compute the coefficients, obviously, is by substitution. You say, I have a polynomial with 3 variables, you have a polynomial with 2 variables, but if I substitute like this, then I can actually produce from my polynomial your polynomial. So this is a very special case of this. And so when we studied this, and only when we saw those two, or we had actually, this was explicitly in one paper, but this is implicitly in many papers, but not explicitly spelled out. So we saw this, you know, people have this argument, sometimes they use this argument. So then it came natural to ask, maybe this is the same. And indeed, here is a theorem. Theorem again, the difficulty is not proving the theorem. If I tell you the theorem is true and you go home and you forgot the proof and you are patient enough, you will find your proof yourself. But you have to look at this. So it says that actually Q is more expressive than P is the definition of dP. If and only if Q, from the coefficients of Q, you can uniformly compute the coefficients of P. And this is obvious. I mean, the coefficient case is more general than the substitution case. Now, how are the classical, the animals in my zoo defined? Well, we have counting generalized colorings, and some of them may enter the zoo. We have many cases of generating functions, the matching polynomial, but the clique polynomial, independence polynomial. We have seen, or maybe we haven't seen, but we have seen graph polynomials of the form sum over A subset of E. This has a name, Z of G x y equals x to the size of A times y to the size of the connected components of the spanning subgraph of A. And then we have a polynomial C of G x, y, z equals sum over all A in E. Same things here, x to the A, y to the k of G, A, and z to, I'll tell you in a moment what this is, C of G, A. And K is the number of connected components, and C is the number of connected components which do not contain isolated points. So these are connected components where every vertex is covered by an edge. Now you can easily see that this polynomial is stronger than this. By taking z equals 1, you get back this one. But what I promised you yesterday, so this one happens to be the most general polynomial for deletion, contraction, and extraction. And it has also the property that with a different sign of substitution, you can get the matching polynomial back. So when I formulated yesterday the Bolobash-Peabody-Riordan conjecture, whether almost all graphs are Tutte unique, here is a conjecture which I will pronounce, maybe it gets my name, that this polynomial, or at least check, but this is a weaker conjecture than Bolobash, show that almost every graph is C unique for this particular polynomial. And if you can't answer this, then you may add one more variable and some parameter here and try for something like this. So anyhow, polynomials like this is the Pot model in statistical mechanics, and it's dp equivalent to the Tat polynomial. And so these are called subset expansion formulas because it gives you kind of a statistics. It associates with each graph a table. The fact that this is a polynomial is not so important, but a table which gives with every subset A the value of those three parameters. And it asks, if you have this complete table for every subset, you know the value of those parameters, whether this allows you to reconstruct the graph from this, and that you encode this table in this way is totally irrelevant. Obviously, you can take, instead of x, you can take x squared to the power of a, and for y you can take 1/3 of y, and I don't know what else. So the way you do this is irrelevant, but basically here you have this table. So these are called subset expansions. Recurrence relations we have seen. I mean, the Tat polynomial or the chromatic polynomial can be written as a recurrence relations. And then there is something I don't talk here about, but Lovász has a big theory. Lovász and Nesetril and other people have a big theory on counting weighted homomorphisms, and each of them also gives a nice graph polynomial. So yes.
In the previous page, yeah. So in the last line, is it
the function? I don't write here the function. The function can be anything. It doesn't have to be computable. It doesn't have to be.
But the next one, if P is less than Q by coefficients computation,
then
isn't it the other
no,
way around?
it's the other way around. You're right. Yeah, sure. Correct. Another mischief of my devil. Okay, yes, it's the other way around. So you see, I mentioned, but I won't go deeply into this. I mentioned the case that the chromatic polynomial, you can compute it, but I all of a sudden had to say, but x0 has to be rational to make it in the Turing model of computation. But this is not very natural. I mean, if you do this type of reductions and you look at the proofs of certain reductions, you really would like to do the same for real values or for complex values, and not just in a funny way. So there is an alternative model of computation which is called BSS, Bloom-Shoup-Smale complexity, and you can try to put the computability of graph polynomials into this model, and this has many advantages, but it has also other disadvantages, especially that the complexity theory here is not as well developed. So I have a paper with my former students where we discuss the advantages of these problems. If you want, I'll print out a version for Professor Ullman, and those who are really interested, I can give you the reference for this. But this is not the topic of today. So the last thing I want to say about this is I want to show you how this generalized chromatic polynomial does capture the matching polynomial. So I want to show all the notions I have developed so far by looking very carefully at the matching polynomial. Not only this, so I already told you that the matching polynomial has a very rich literature. It has application in chemistry and in physics of ferromagnetism. The mathematical theory you find here, the chemical theory you find here, and the application of the chemical theory you find in Garrett's book. You have seen this before. So let's repeat. So the historic first matching polynomial, which appears in a paper by Hellman and Lieb, the names were before, somewhere on our slide, is called the acyclic polynomial, or the matching defect polynomial, and it has been written like this. So -1 to the k, the number of k matchings, times x to n minus 2k. But actually, what is this x n minus 2k? N is the number of vertices, and 2k is the number of vertices used by a k matching. So this is x to the power of the number of vertices which are not covered by the matching. Okay? And for some reason, this is what they wanted. Now, the mathematician who doesn't have applications in mind, he would have immediately written this polynomial or any other basis here, but he wouldn't have introduced this thing here. Anyhow, so this appears in the literature, and this appears in the literature, and you can see that one can be computed from the other by this equation, but the equation here depends on a value which depends on the graph. N is the number of vertices of the graph. So we note in the terminology of before that if you know the coefficients of this, you can compute the coefficients of this by substitution, but the other way around you cannot, because here you have to know the number of isolated points, and here you don't get the number of isolated points. Okay, so this shift actually is important. Now the 2k is not important. You could have taken here n minus k or n plus k or multiply x to the power n in front of it or something. But the main thing is that this ignores the isolated points, and this doesn't ignore the isolated points. Now, in the original paper, actually, they looked at the bivariate version of the matching polynomial, and it does it was written like this: number of matchings of size k times y to the power k x to the power n minus 2k. So these are the number of edges used in the matching, and these are the number of vertices, x to the number of vertices not used in the matching. But actually the two variables are related to each other, so the two variable is not much stronger than this, but now you can write this. I want to do this later. So instead of summing over k, you can sum over a, where a is a matching, and you just write x to the power of size of vertices of G minus size twice the size of A times x to the size of A. So you have a sum, you get close to the form here, but you have an additional property here. A doesn't range over all subsets of edges, but only on certain edges. But again, you have this x to the power of a parameter and y to the power of another parameter. So this can be viewed as a generating function of a special kind. It also can be viewed as a subset expansion of a special kind. And you have substitutions like the m can be obtained from the big M by substituting for y minus 1, and the g can be obtained from the big M by substituting for the first variable 1 and for the second variable x, or however you name it. So anyhow, to get to the notion of substitution instance, this was the traditional case. The M covers both cases, and each of them is a substitution instance. So now, my friend Zilber didn't know anything about graph polynomials, but he said, that the matching polynomial, which I showed him as an example, was a special case of the general chromatic polynomial. So I said, how come? So he said, okay, let's do it the following way. And we do the two-variable case. So we have two sorts of color, which will be the role of the variables, the K1 colors and the K2 colors. And the coloring property, which consists of a 5-tuple, where you have the number of vertices of the graph, you have the edge relation of the graph, you have the two naked sets for the colors of the first type and the second type, and you have two coloring relations, R1 and R2. So R1 is a subset of edges times colors, which happens to be a function, but anyhow. And R2 is a subset of vertices times the second type of colors, such that R1 happens to is a partial function, the domain of which is a matching of G. So R1 is a partial function, and the domain of R is a subset of E, and you write down it satisfies the property of being a matching. And R2 is a relation, is a partial function with domain V minus the things which are not covered by the matching. And then you see that this is a coloring property in our abstract sense. So you have two coloring relations, and there is a bound here on the condition, and you have these two colors, and this satisfies the extension property. So the number of pairs R1 and R2 which satisfy those red properties is a polynomial in K1 and K2.
So this time it's slightly more general because you allow.
Now I allow relations, yes.
The colors to be
yes.
Two sets.
Yes. So yes, it is kind of a force, but I mean, he knew about this because in his model theoretic application he had looked at many cases like this, but he didn't know about graph polynomials. So when I told him I'm studying graph polynomials and I gave him a definition of matching polynomial, he immediately saw that he can write the matching polynomial like this, and therefore the matching polynomial is, in our sense, a generalized chromatic polynomial. And this proof is generic. I mean, once you understand what is going on here, you can do this for any generating function and for the Tat polynomial and everything. I mean, actually we proved, but I will have to need logic afterwards to make precise, but in a hand-waving way we have shown that every reasonably defined graph polynomial actually is a generalized chromatic polynomial. And this will make more sense after I teach you some logic. So but actually this trick works in general. So you give me any graph polynomial in the literature, if I don't have to make precise the framework, I claim that I can bet with you will not be able to find the graph polynomial in a fixed number of variables which I cannot forcefully reformulate in such a way. So in this sense you can say that every reasonably defined graph polynomial happens to be a generalized chromatic polynomial. Okay, we can, if you want to have a 5-minute break, we can have a 5-minute break.
You like it?
You like it? Huh? You want 10 minutes break? I don't know. I should be back in the